In module 10, we introduced BIBD and we had some understanding about the parametric relations, the analysis aspect, and the expression for the variance of estimated treatment differences, and why the name balanced is coming in the full explanation of BIBD, namely balanced incomplete block design. So basically it is a connected, proper, equireplicate binary design with constant variance for the pairwise treatment difference contrasts estimates. That is why the name came, and we also talked about little bit about the combinatorial properties of the design. But as I said, there is much more to know about the BIBDs, mainly the constructional aspect. So in this module, we will be discussing some aspects of how to construct the designs, and when we know that the design is virtually impossible, it does not exist, even though the parametric relations are in order, still it may be that you simply don't have any design of that type. So we are going to take up these issues, and at least one or two methods we are going to explain, describe regarding the construction of BIBDs. So for the BIBD, we have already noted that the expression for the variance of the estimated difference between a pair of treatment effects is given by 2 sigma square by r multiplied by a constant factor, which is k into v minus 1 over v into k minus 1. So now we may go a little further from here. So the first part, 2 sigma square by r, that is an expression for the variance of the treatment, estimate of the treatment difference in the context of a CRD with replication R, or in the context of an RBD with replication R. Because the RBD is an orthogonal design, so there is no difference between the expression for the variance for CRD as against RBD with the same replication parameter R. Therefore, in a BIBD, the expression for the variance is this quantity 2 sigma square by r multiplied by the constant factor k into v minus 1 over v into k minus 1. This constant factor is denoted by the letter E, and it is referred to as the efficiency of the BIBD.
Sir, I can see tremendous simplification in the reduced normal equation for estimation of tau contrast. Now it transpires that tau hat is equal to q by E, so that tau I hat minus tau I prime hat is equal to qi minus qi prime by E for all treatment pairs, and for the sum of squares of treatment also simplifies to sum over qi square by E. We are now in a position to prepare the ANOVA table for testing the hypothesis involving tau contrast. Further to this, we can easily construct the extended ANOVA table for testing the other hypothesis related to block contrast. I believe this is what is referred to as intra-block analysis of a BIBD. Maybe that is because within every block we are working with observational contrasts to obtain information on the pairwise treatment effects differences, and that seems to be the only source of information for treatment effects differences. Am I right, sir?
Yes, very much so. It has been proved that for given design parameters B, V, R and K, if there is a BIBD, then it will provide constant variance for estimates of all pairwise treatment effects differences. That's what we saw earlier.
Yes, sir.
No other design will have this feature. It is an if and only if statement. That's why a BIBD is referred to as a balanced design.
Okay.
That clarifies its expanded qualification in terms of a balanced design.
Okay.
So in effect, it is a variance balanced design, binary proper equireplicate incomplete design.
Sir, would you also explain why such designs are combinatorially challenging to find, and if indeed plenty of BIBDs are in fact available to practitioners, why should a practitioner at all bother about looking for and then using a BIBD given the design parameters B, V, R, K?
Yeah, Sagorika, thanks for raising these issues. Yes, you have got all questions in the right spirit. We will be discussing these points one by one. That BIBDs are combinatorially challenging to find should be clear as soon as we are talking in terms of high values of the design parameters. When you take a very simple example like B equal to 6, V equal to 4, K equal to 2, R equal to 3, we can carefully build upon the definition and we can see that a BIBD with these parameters does exist. It is very trivial to construct. Take all pairs of treatments. Again, when B equal to V equal to 21, R equal to K equal to 16, lambda equal to 12, it is almost impossible to get any clue as to the existence of the underlying BIBD if at all. Of course, we can verify the combinatorial relation, parametric relation, namely Bk equal to Vr, that is trivial, and lambda into V minus 1, which is 12 times 20, which is 240, R into K minus 1 is 16 times 15. So apparently you don't see any contradiction, but absolutely you have no clue as to whether you can really construct a design with these parameters or not. So these are the intriguing issues that come up. There we need help, we need deep combinatorial arguments, and in this context, the theory of Galois fields and related constructions of mutually orthogonal Latin squares have been found extremely useful. These are all regarded as pioneering contributions of an Indian mathematician, cum statistician R.C. Ghosh and his associates. Below we take up the above two examples and provide step-by-step solutions. For the BIBD with parameters B equal to 6, V equal to 4, R equal to 3, K equal to 2, lambda equal to 1, we have immediate solution. As I told you, just start writing pairs of treatments. Choose pairs of treatments and form the blocks with each pair, that's it. Here we use complete set of mutually orthogonal Latin squares of order 4. For the second example, let's go back to the combinatorial problem. For the second example, which involves B equal to V equal to 21, R equal to K equal to 16 and lambda equal to 12, I will take it up and I will thoroughly discuss all the steps that are coming up in the construction of this design. This design does exist and is a highly non-trivial combinatorial construction. Let us go slow on it. So first thing is we start with complete set of mutually orthogonal Latin squares of order 4. L1 is the first Latin square of order 4. L2 is the second, L3 is the third, one involves the numbers 1, 2, 3, 4, other involves the Greek symbols alpha, beta, gamma, delta, other involves the Roman symbols A, B, C, D. These three are mutually orthogonal in the sense that if you superimpose L2 on L1, then you can find 1 alpha, 1 beta, 1 gamma, 1 delta, 2 alpha, 2 beta, etc. All combinations will come up exactly once in the superimposition. Same with any pair. Therefore, these are called mutually orthogonal Latin squares. So we have a set like this which involves altogether 4 symbols in every Latin square. Now we first construct the BIBD with B equal to 20, V equal to 16, R equal to 5, K equal to 4, lambda equal to 1, using the modes as shown above. So for that, basically we start with a 4 by 4 natural square. So this one is a natural square, 1, 2, 3, 4, 5, 6, 7, 8, etc. This tells you that you are dealing with 16 treatment symbols over there, V equal to 16. We treat the rows of this square as forming the first set of 4 blocks. Now in the BIBD that we are referring to, there are altogether 20 blocks involving 16 treatments, and the block size is 4, so every block will have size 4. Starting with this natural square, we take the rows of the square, they form the first set of 4 blocks. Then we take the columns of the square and they form another set of 4 blocks. So the first set of blocks are obtained by taking the rows of the natural square and the second set of 4 blocks are obtained by taking the columns of the natural square. Those are written as rows here.
Yes.
We still need 3 additional sets of 4 blocks. Those are formed with the help of the mutually orthogonal Latin squares of order 4 that have been displayed above. So the idea is that you superimpose L1 on the natural square and you form blocks of size 4 by identifying the numbers. Namely 1, the number 1 you will identify 4 times in the natural square. The number 2 also you will identify 4 times in the natural square. Identify the numbers and start forming blocks. For example, when we look to the first Latin square L1 and we superimpose L1 on this natural square, we find that the number 1 appears with the numbers 1, 7, 10 and 16 in the natural square. The number 2 of L1 appears with the numbers 2, 8, 9, 15 in the natural square and so on. Therefore, we form the third set of blocks by referring to the numbers in the Latin square and by identifying their corresponding numbers in the natural square. That is how we get the 4 blocks here: 1, 7, 10, 16, 2, 8, 9, 15, etc. Next, we superimpose L2 on the natural square and I will identify the 4 symbols of L2, namely alpha, beta, gamma, delta, with the numbers in the natural square, and we find that alpha corresponds to 1, 8, 11, 14 in the natural square, beta corresponds to 2, 7, 12, 13, like that we have these 4 rows again forming the 4 blocks of the BIBD. Next one is we have to superimpose the third Latin square L3, and in the above format we find out the last set of 4 blocks 1, 6, 12, 15, etc. So that is how altogether now we have a solution to the BIBD involving 20 blocks, each of size 4. Every treatment occurs exactly 5 times because in every square, in every formation, every treatment occurs exactly once and there are 5 formations. Therefore, the treatment application is 5 and one can see that any pair of treatments they occur together exactly once. So this gives us a BIBD with parameters 20, 16, 5, 4, 1. But now we need to provide one more step to be able to get to the BIBD that we are referring to.
Sir, this is definitely interesting. I can see that you must be referring to a general theorem along this line. Now, you must be relating the above BIBD to the one you ultimate want to arrive at. I see for the BIBD with 21, 21, 16, 16, 12, you need block size 16 as against 4. One way would be to consider what I would say as a complementary design, meaning thereby that you work with the complement of every block. Let me see what I am up to. Starting with the BIBD with B is equal to 20, V is equal to 16, R is equal to 5, K is equal to 4 and lambda is equal to 1. If we go for complementation, we end up with B star is equal to B is equal to 20 blocks, V star is equal to V is equal to 16 treatments, R star is equal to 15 and K star is equal to 12. What about constancy of the lambda parameter? Yes, that holds as well with lambda star is equal to 1. I think 11, sorry. I think I can argue this out.
Okay, so we will continue in the next module.
Okay, okay.
Very good. So we have to complete this part and then we will see what else is coming up.
Okay, sir.
Good. Sagarika, so basically in module 11, we talked about BIBDs. We took up 2 simple examples, one with a small combination of the parameter values BV, RK, lambda. Thereby it was very easy either to see yes or no to the construction, and we could see the construction right away. Other was less transparent, less obvious. It involved the parameters in a big way, and we needed to understand how the thought process should go while constructing this design, if at all. We have come almost towards the end by taking up a basic working design, a BIBD, by using the concept of mutually orthogonal Latin squares and then by using them in constructing a BIBD, and still we have not reached till the end, that will hopefully come up in the next module. And meanwhile, we also talked about the analysis aspect, and when we took up the BIBD in terms of the questions, we thought of a generalization of BIBD in combination with RBD to what is called a balanced block design. So, balanced block design is a combination of BIBD and RBD. That's what we discussed. And then we also thought of complementary design of a BIBD, and then the dual design of a BIBD, and we tried to understand how far complementary and dual designs would still be BIBDs in general. So these are some of the things that came up in this module. Let's see what we have in the next module. So Sagarika, at this stage, let us take up some questions and MCQs.
Okay, sir.
So while we proceed with the construction in the next module, meanwhile we can take up some questions.
Okay, sir.
Please.
Sir, a balanced block design is a combination of an RBD and a BIBD. If the BIBD has parameters like BV, RK, lambda, and if the RBD is repeated S times, then BIBD has BBD has the parameters capital B is equal to B, capital V is equal to small v, capital R is equal to small r plus SB, and capital K is equal to small k plus SV, where each block of the BIBD is extended by S copies of the RBD with V treatments in B blocks. Thus, block size is extended to K plus SV. So, from this there are three questions. The first one is we need to provide intra-block analysis of a BBD and display the ANOVA table. So, this is the first one. The second one is we need to work out explicit expressions for variances of estimated pairwise treatment effects differences, and for the third one we need to justify the name balanced here.
Okay. So as you can see, this BBD, balanced block design, it is an extension of BIBD.
Yes.
In every block of a BIBD, we are extending the block size. From K, we are making it K plus a multiple of V, S times V.
Yes, sir.
So we are incorporating all the treatments in every block, extra S times each. Thereby the block size is extended from K to K plus SV. If that is done, then what we get is a BBD, which involves BIBD and S copies of the RBD. That is the whole idea. Once you have it, now you go back to our general analysis of a block design, refer to the C matrix, you work out the C matrix for this design, you show that the C matrix has an obviously nice simplification, and you can work out the expression for sum of squares, everything can be done. So once you see the formation of the capital N matrix, and then you can work out C and you can provide the entire analysis.
Okay, sir.
Note that we are all the time talking about the treatment sum of squares adjusted and block sum of squares unadjusted. Okay, that is how you get it.
Yes.
And once you have the expression for the C matrix C plus, you justify that C plus matrix. C matrix has all the positive eigenvalues equal, and therefore C plus has the same property, and hence all variance estimates of all the pairwise treatment contrast will have the same variance, and that is how the justification of the name balanced will come.
Okay.
It is a generalization of BIBD. If the block size is more than V, then you can think of a BBD extending RBD and extending BIBD. That is the whole idea.
Yes, sir. The first one is for a BIBD with parameters BV, RK, lambda to exist. It is necessary and sufficient that there are four choices. B is always greater or equal to V, V is more than K, R into K minus 1 by V minus 1, and none of the above. These are four of the
maybe
options.
question number C seems to be incomplete.
Yes.
That should have been R into K minus 1 over V minus 1 is an integer.
Yes, sir.
And question number D, the option number D is none of the above. But we have already seen earlier that even though these combinatorial identities are relations are satisfied, namely Bk equal to Vr and lambda into V minus 1 equal to R into K minus 1, it is not necessary that a design will exist, okay? So you have to keep that in mind, okay? This is a very strong statement, necessary and sufficient. So you have to be careful.
Okay, sir.
What is the next question?
The next one is a BIBD with parameters PV, RK, lambda exists if and only if the dual design, which is obtained by interchanging the roles of blocks and treatments, is also a BIBD. And the two options are true. The statement is true provided B is equal to V, and the second one is it is always false.
That's an interesting problem. So let's see, you are given a BIBD and then you interchange the roles of blocks and treatments and you come up with another design. That derived design will also be BIBD provided this thing happens. Now, when you interchange the roles of blocks and treatments, what happens is the incidence matrix capital N, it changes to N transpose. Naturally, in capital N you have treatment cross block incidence. The moment you interchange their role, it becomes block cross treatment. So N changes to N transpose. And then you have to figure out if with this change, the new design that you get, if that is still a BIBD, and for that to happen, is it that it will be true provided B equal to V, or it is always false, it can never be true, etc. Okay?
Here is the third one. Complementary design of a BIBD is a BIBD with the same set of parameter values. This is the statement is always true, this is sometimes true, and this can never be true.
Let's see. Complementary design means in any block, whatever treatments you have, you take the complement of that. So the block size was K, now it becomes V minus K because the total number is V. Therefore, now from a BIBD, if I take the complementary design, it goes on the other side and that has got block size V minus K. That's the first thing that is happening. The complementary design is a BIBD with the same set of parameters that necessarily means K equal to V minus K. So V has got to be equal to 2K. So that is a condition that is needed for the BIBD. So this cannot be always true because you don't necessarily have V equal to 2K. It can be sometimes true depending on whether V equal to 2K or not. So suppose V equal to 2K, does that mean that the complementary design is still a BIBD? That is what you have to figure out. First thing is, unless V equal to 2K, it cannot be. So sometimes it may be true if V equal to 2K. Even if V equal to 2K, is it a BIBD, the complementary design? That's what you have to figure out. Okay? Then your answer will be either B or C.